In this video, I will be talking about measures of variation. The first measure of variation is the range. The range is maximum minus minimum of the data set, or the highest minus the lowest value. So for short, I'll just write this down here. And we talked about finding the range when we talked about finding the class width. This is actually the first step in trying to create a frequency distribution, finding the range, and then using that to finding the class width. So you all know what the range is. Just simply take the largest value and subtract from it the lowest value. However, the range is not taking into the account all data values. So it is a measure of the variation, but not good enough. And that's why we are looking for a measure that will take into account all data values and will tell us a little bit more of what is going on inside the distribution. The next value that we'll be talking about is called the standard deviation. The standard deviation, it's actually the average distance a data member is from the mean. So let's see, what does this mean? I will write down the formula. However, we will do most of this using the calculator. But just for you to know the formula and the notation, the standard deviation is summation of x minus mu squared divided by capital N, and take the square root of all of this. So this is the formula, and this formula is used when we are talking about the population. This is sigma. It's a Greek letter. You may recognize this as not being a Roman letter, so it is a Greek letter. And I'll write down again, this is used when we use a population. So this is actually a parameter. This is a notation for the standard deviation. You do realize that what I'm doing right here is using the population notation. Mu is the mean of the population and N is the population size. So let's just quickly write this down. X is any data value or data member. Mu is the mean, and we know it's the population. It represents the population mean, and N is the size, the population size. So what I will do next, I will write down the corresponding formula, but this time I'll be using Roman letters. Here we go. This is the symbol that is used for the standard deviation. When we try to find the average distance, a value is from the mean, and I will change the notations accordingly. Look at this. This is x bar, which is the sample mean. And the formula is adjusted a little bit. It is n minus 1 on the bottom. Don't forget about the square right here. And this is just the Roman letter S. So that means we are talking about the standard deviation of the sample. Okay. However, we will not be using these formulas because we will be using the calculator. There is value in trying to plug in formulas, trying to understand how the formulas work, which is okay. You can go ahead and practice with that. There are a lot of examples in your textbook. However, this class is based on using technology. We'll learn how to use the calculator and we'll practice a little bit later. First, let me make sure we write down here that x bar is the mean. And again, and note, this is the mean, this is also the mean. But the first one is the mean when population is used. This one is the mean when sample is used. And N, lowercase n, is the sample size. Now, before we go ahead and practice, I want to point out the next measure right here, which is the variance. Now, simply said, the variance is actually the first thing we find in trying to develop the formula for the standard deviation. So the variance will actually be the standard deviation squared. You can see that right here. This is the symbol when we use population, and this is the symbol when we use the sample. The formulas are actually the exact same formulas without the square root, because of course you take the sigma and square it. That means you will get rid of the square root. So let's go ahead and do an example. There are actually two examples right here. I'll go ahead and use the calculator to figure out the results for example 1. And feel free to practice with example 2. here we go. And before doing that, so I will write down the calculator steps right here, and we'll go ahead and do that. So in the calculator, you'll have to simply plug in the data. We know how to plug in the data. And again, we are doing TI-83, TI-84 calculator. We're using that calculator. Let's plug in the data. So click on Stats, Edit, and plug in the data in one of the lists. I usually use list 1. Then go ahead and click on Stats again, but this time click on Calc. And under Calc, you should click on 1, which is 1 variable stats. We've done this before when we found the measures of the center, meaning the mean. And on that screen, you will see a lot of information starting with the mean, and then some summations, right? And scrolling down, you will see SX, and you will also see sigma F. I will actually enter my information in list 3. Okay, you can enter it. You should enter it in list 1 if you have nothing in there, but I will be using this example a little bit later, so I don't want to clear that list. So in list 3, I will simply enter the first example. You see it right there on the screen: 49.5, 57, 66, 73, 78, 85, and 92. Okay, and now that I have my information in this list, I'll go back to Stats and get to Calc using arrow. 1 variable stats. This is okay. I'll hit Enter. And my list is list 3. So I will simply do second 3, push second 3. Want to make sure I will have nothing on my frequency list, and hit Calculate. If you do not have this screen, then when you do 1 variable stats, if you don't have your values in list 1, you have to make sure you specify the list. So make sure if you have your values in list 3, you push second 3, you have to specify the list. And then you hit Enter. And this is the information I get. I get the mean and all the other information. Here is what I am interested in: SX and sigma X. SX is the standard deviation of the sample. Sigma X is the standard deviation of the population. So in this case, we have S equals, or actually I will approximate that as 15.12, and sigma is 13.99. Well, actually, round to 2 decimal places, it will be 14. Okay. Scrolling down, you see some other measures, and we'll be talking about these measures in the next video. These are measures of locations or measures of position. Now we use S if we look at the data and we think of this as a sample. This is a sample. We use sigma if we look at the data and we know that is the entire population. Most of the time, if they don't say in the problem that is the population, you do not really use this value. Most of the studies are done on samples, so this is the value you will be looking at. And now I will get back here and write down this information. So these are the results of the first example. On the calculator, you should have these values for the mean. And then for the standard deviation, for sigma, we have rounded this to 14. These are all rounded values, right? Because we have decimals, we need to round. And for the second one, which is S, it's 15.12. Now to answer this question related to the variance, we simply have to take the number and square it, sigma squared. Or we have to take the S and square it. And I'll let you do that. Just keep in mind, if you know standard deviation and you have to find the variance, you will square the number. If you are given the variance and you have to find the standard deviation, you will square root the number. Okay? So for example, I'll just give you an example right here. If this one is given, if the variance is given, and I'll just come up with this example, and the question is, find the standard deviation, you simply have to realize that sigma squared is 12. That's the variance. So to find sigma, you'll simply square root that 12. Okay, I hope this makes sense. And we will continue with this example. Let's see, how do we find the standard deviation if we have group frequency distribution. This is the example I used on the previous video, the video related to the measures of the center. So here we go. The only difference between what we've done before with this example is right here. On the previous example, we had to find the mean. On this example, we have to find the standard deviation. So actually, the standard deviation was on the screen when we found the mean. And in order to find these measures, all we do is get an approximation of where the data values are or what the data values are, the best estimate we can get for the data values by creating another column, which is the midpoint. So right here, we have the midpoint of each class, and the midpoint of the first class is 31, and then we have 36, we have 41 and 46. In order to find the standard deviation, we will simply plug this in the calculator in one of the lists. I'll be using list 1 for this one, and the frequency in the other list. So all we need are these two lists, the frequency and the midpoints. Again, following the same procedure, we get one variable stats after we enter the information in those lists. And very important right here, make sure you have L1, comma L2. You use this if you do not have the screen where they ask you about the frequency list. If you do have the screen with the frequency list, just enter list 2. Here is how this works. I will get to my list. I already have the data in here. So under edit, it's in my first two lists, okay? So using these two lists, I'll go to stats, I'll go to calc, one variable stats, get here, make sure you have your list as the list with the data values, and my values are in list 1 this time, so I'll do second 1 to get my list 1 in there, and for the frequency list, I have to enter second 2, and now calculate, hit enter. The standard deviation for this will be S, which is 5.33. Now, if these 30 small cars samples is considered a sample, then we will be using S, and we will look at this as a sample. But otherwise, if they somewhere in the problem will state that as the population, we have to use sigma. So the information we got from working with a calculator is that S, which is the standard deviation in this example, is 5.33. And again, I will be estimating this, and I'm looking at this as a sample. That's why I am using S. Here is another example that I will let you do. And after you use the calculator, the result will be as approximated as 8.48. So check on that. And now I will focus on showing you some applications of this very important measure, which is the standard deviation. One first application applies actually to the z-score. The z-score is actually a measure of location or measure of position, but this measure is based on the number of standard deviations a value is from the mean. So this is where the standard deviation appears. How many standard deviations a value is from the mean? What does that mean? Well, let's just take a look at the formula, and this is a very important formula. We will be using this quite a lot in this class. A value is from the mean. This is the distance between a value and the mean, right? And in terms of how many standard deviations, we have to simply divide this by S, by the standard deviation. Now, you realize that I wrote this formula in terms of statistics. If I want to write this formula in terms of parameters, I'll simply adjust my notations. Now, let's just take a look at this example. The average test score of Mr. Jones' class is 124 with a standard deviation of 16. The average test score of Mrs. Siegel's class is 72 with a standard deviation of 8. Tina and Melanie were comparing themselves to see who did better on their prospective exams. Tina scored a 118 in Mr. Jones' exam, while Melanie scored a 67 on Mrs. Siegel's exam. find the z-scores, and compare. So you may need to read this information again. Just stop the video and read the information. And make sure you make a habit of writing down the given information like this. For example, I have Mr. Jones' class and I have Mrs. Siegel's class. And related to Mr. Jones, I have the average, and I'll be looking at this as a sample, so I use the sample notation. And I have the standard deviation, which is 16. So these two values related to this class. Now from Mrs. Siegel, I have an X bar, which is 72. And I also have a standard deviation, which is 8. Now, Tina is a student in Mr. Jones. So I'll just simply write down Tina and her score. This is a data value, an X. Her score is 118. Melanie is in Mrs. Siegel's class and her score is 67. The question is, find the z-scores. Well, why do we need to find the z-scores? Well, right away we realize that we cannot compare, we cannot know who did better, because Mr. Jones has a scoring system, Mrs. Siegel has a different scoring system. It's like comparing apples and oranges. But the z-score will allow us to compare the results. So let's find Melanie. Well, actually, first we'll find Tina z-score, and then Melanie's z-score. Tina's z-score will be z, and I'm simply applying the formula right here. So I look at the information for Tina, and I have 118 minus 124 divided by 16. If you take the calculator and figure this out, if you do it all at once, make sure you put this on the parentheses, otherwise you'll make mistakes. You will get, round to 2 decimal places, this value for Tina. This is her score, okay? Now let's just do the exact same thing for Melanie. And for Melanie, we have 67 minus 72 divided by 8. And again, if we use a calculator and do that, we will get negative 0.63. And now we have to compare these two results. How do we compare these two results? Well, we simply take the number line and see which one is larger. Keep in mind, we are dealing with negative values. So the one that is closer to 0 will actually be larger, because this is a number line going from left to right. Let's just say I have a 0 right here, and I have a very large scale of 1 to the left, which makes this a negative 1. I'm looking at negative 0.5 here, just to be able to put these numbers in. I see Tina's score, which is, let's just assume I'm estimating here, but it will be somewhere around here. And I have Melanie's score, which is somewhere around here. So the one that is actually larger is this value, which is Tina. So the answer for this problem will be, based on comparing the z-scores, Tina did better, okay? Just keep in mind, when you look at these results at a class and you compare Tina with the rest of the class, Tina did worse than the average score. Well, actually the same thing happens with Melanie. Melanie's score is less than the average, so she did worse too. So how do we compare later? Because her score is less than the average, when you apply the formula, the z-score will be negative. So the z-scores are on the left of 0. Now the z-score will be positive if the individual data value is greater than the average. We will spend more time on the z-score, but for now, let's move on to the next application. Here we go. The empirical rule. The empirical rule is a very important rule that is used when we deal with symmetrical or bell-shaped distributions. It's the most commonly used, but also the most abused distribution. And I write down here it should be used for symmetrical distributions only. Unfortunately, because it's simple to use, people are using it regardless, and that's not the purpose of this, that the results will not be true. The empirical rule tells us that 68% of the data lies within one standard deviation of the mean, 95% of the data lies within 2 standard deviations of the mean, and 99.7% of the data lies within 3 standard deviations of the mean. What does this all mean? Well, let's just try to visualize what this means. And I have this graph right here. Look at this distribution, which is a bell-shaped, and think of all the area under the distribution as 100%. Area equals to 100%. Okay, of course, half of it up to this point, it will be 50% and so on. Also, keep in mind that this, we call these tails. These tails will not really touch the x-axis. You will always have data right here on the bottom, okay? And you want to make sure you make sense of what is going on here. You will put the data on the x-axis, then look 1, 2, and 3 standard deviations above and below the mean. I have an example right here just to visualize it with specific numbers. Let's just say the mean is 40, so I'll put 40 right here. So 1 standard deviation above the mean, I will find the value 43. Now, how did I get there? Well, think of this scale as the standard deviation. I simply add 3. The standard deviation works this way. When I say 1 standard deviation, I add 3. When I say 2 standard deviations, I'll keep adding that 3, or I add 3 2 times. And that next number will be actually here 46. And then I'll have 49. Moving down, I have 37. I have a 34. And I have a 31. Okay? So what this beautiful theorem tells us is, so the theorem tells us that 68% and 68% of the data will be right here under the curve. This blue shaded area is between this and this, between 2 values. So basically 68% of the data is in this interval. And then moving on, same thing, 2 standard deviations from the mean, we have 95% of the data. If you think of that, that's a lot. Between 34 and 46. So you know a lot about the data, that 95% of the data being in this interval. Now moving far away from the mean, well, actually 3 standard deviations from the mean, we have 99.7% of the data. If you think of that, 99.7% of the data is almost everything. Practically, it's everything. Theoretically, it leaves room for a little bit, just a little bit right here in this opening. 99.7% of the data. With these numbers, you'll have to remember, this is something that you will have to actually memorize. This is called the 68, 95, 99.7% rule, okay? And of course, the intervals associated with this. 1 standard deviations from the mean will have 68% of the data. 2 standard deviations will have 95% of the data, and 3 standard deviations from the mean, we have 99.7% of the data. And now let's take a look at another application. Here is the next application. The average height of adult men in the United States is 68 inches with a standard deviation of 2.5 inches. So I'll write down the given information right here. And I'll be using mu because they say in the United States, so that will be the population. And the standard deviation, I'll be using the corresponding symbol, which is sigma. That's all I need to answer the following question. Find the heights of the middle 68%. First of all, the distribution of heights of adult men is a symmetric distribution. And I like to use a lot of room to get my visuals. So make sure you have a large visual, okay, for to answer each one of these questions. And I will do 1 for each question. So here we go. I have to look in the middle 68% and find the heights. Keep in mind, this is where I have my data. And what I know so far is that this number right here is 68. This is the mean. That's where everything starts. And I have given the middle 68%. So what do I know about the middle 68%? I'm thinking back at the empirical rule. Know that this is corresponding to the values located 1 standard deviations from the mean. That's all I need to find. 1 standard deviation from the mean. Well, I'll simply find those values by adding 2.5, which will be 70.5 right here, and subtracting 2.5 from 68, which will be 65.5. So these are the heights corresponding to the middle 68%. So I would say 68% of heights is in this interval or between these two values. Next question. Now, this time I'm asked to find the percentage of men, which percentage of men is taller than 73 inches. So I will do the same kind of graph, and I will try to see how I apply the empirical rule. Here we go. These are the heights. And right here in the middle, I have the 68, which is the mean. And I try to focus now. So this is for this, okay? Try to focus now on 73. So I'm trying to see where is 73. Well, it will be to the right of the mean. I'll go by 1 standard deviation, and then the second standard deviation. Okay, and I think I arrived at the 73, okay? I can go a little bit higher, which will be 75.5. Let's just do this just to be consistent. On the other side, 65.5, then subtract again 2.5, it's 63 and 60.5. So what I have is 1, 2, 3 standard deviations above and below the mean. So I am interested in the percentage, meaning the area under the curve, which is greater than. What I will do, I will simply shade that area. This is what I'm interested in. And there are different ways of doing this problem, but most students will do it this way. They will focus on the fact that this is 2 standard deviations from the mean, and this is also 2 standard deviations from the mean. What we know about values located to standard deviations from the mean, they correspond to 95% of the data. So right here, I have 95% of the data. So most students will start this problem with subtracting the middle 95% from 100%. This is only the first step of the problem because you must realize that right here, we have an area which is equal to this area. So the 5% should be split in 2, and you will get the answer, which is 2.5. So make sure you split this in 2, so it will be 2.5%. This is one way of doing the problem. There are different ways of doing the problem, especially if you consider the portions from which this area is formed. Like, for example, because this is a symmetrical distribution, and I'm coming back to this visual, you can actually find each piece by splitting the distribution, the area into 2. And you can do that with the 95%, split the 95% in 2 and get right here the area of 47.5. And then just look at this half, because you're looking at only this tail. This half is 50%. 50% minus the 47.5 will be the same answer, 2.5%. I will let you practice on the last question for this problem, and we will move on. And this is the second topic we want to talk about. It's called Chebyshev theorem. Chebyshev theorem states that the portion of any data set lying within k standard deviations, where k is greater than 1, of the mean is at least this expression. This is a formula. And if you plug in the formula 2, you will get the portion or the proportion or the percentage associated with 2 standard deviations from the mean. And if you plug in 3, you will get this one. If you plug in 4, you will get a different one. So you can plug in different values for K to find out the percentage. You can tell that this is a more general result because Chebyshev theorem applies to any data. So here is what this one tells us. If we have any data, any shape, then we cannot really say what is going on with a spread 1 standard deviation from the mean. Only more than 1 standard deviation from the mean. Keep in mind, K is how many standard deviations from the mean. So as a visual, here we go. We have a skewed distribution. And now the mean, let's just say it's here somewhere. Let's just say that's X bar. 1 standard deviation from the mean, I don't really know anything about this percentage because this one tells me it's too general. I cannot tell you what is going on there, okay? But I can tell you that more than 1, you can plug in the formula and find the results. So here is what they did. For K equals 2 standard deviations from the mean. So I'll come right here, 2 standard deviations from the mean. This one says that at least 75% of the data will be found right here. And if we plug in 3 standard deviations from the mean, we will find at least 88.9% of the data, which is quite a lot, especially given that this is not a symmetric distribution. And of course, you can figure out any other percentage if you plug in the corresponding K. So let's just take a look at an example, and this will be the last thing we have in this video. Chebyshev theorem. It says the mean time in a women's 400-meter dash is 57.07 seconds with a standard deviation of 1.05. Apply Chebyshev's theorem to the data using K equals 2 and interpret the results. So this is what we're gonna do. First of all, we wanna make sure we know that given information is that the mean is 57.07 seconds and the standard deviation is 1.05 seconds. To apply the theorem, I will simply sketch the graph, so try to visualize it, okay? And I'm using a skewed right distribution. You can use a skewed left distribution. However, try to not use a symmetric distribution. And I will simply put the mean in here. Here is the mean, which is 57.07. And I'm looking 2 standard deviations from the mean. So 1, 2. The standard deviation, keep in mind, is 1.05. So I will just simply add 1.05 here to get to the first one, 1.05 here to get to the second one, or I can just take 57.07 plus 2 times 1.05. I'm getting to 2 standard deviations. If you do that, you will get to 59.09. So this value is 2 standard deviations from the mean. And now I will do the exact same thing below the mean. So I will simply take the mean and subtract twice the standard deviation. And that will give me 54.97. Hopefully these are correct. Check these values. Anyway, what I'm interested in is what is the proportion within these 2 values? Well, the proportion under the curve within these 2 values is 75%. I know that because this is a result of Chebyshev theorem. Okay, so how do I interpret these results? I'll simply say that at least 75% of the time in a women's 400-meter dash are between 54.97 seconds and 59.09 seconds. And this concludes this video.